All right, let's dive right in. We're all familiar with the power of machine learning and data science.
Yeah.
But have you ever considered that these models could be unintentionally leaking sensitive information
Uh-huh.
about the very data they were trained on?
Right.
That's the core issue that this paper,
Uh,
Winstein 10.05820, Membership Inference Attacks Against Machine Learning Models,
right.
brings to light.
Yeah.
It's by Reza Shokri, Stronati, Congzheng, and Vitaly Shmatikov.
Okay.
And it really digs deep into how someone could actually figure out if your data
Oh, wow.
was used to train a model just by looking at its predictions.
Just by analyzing its predictions.
Yeah, they call it a membership inference attack.
Interesting. And are these just theoretical attacks, or do they pose a real-world threat?
Well, what's particularly concerning is that they found vulnerabilities even in widely used commercial machine learning platforms
Oh, really?
like Google Prediction API and Amazon Machine Learning.
So this isn't just some obscure academic problem.
Ex-
It has real-world implications.
So how do these membership inference attacks actually work?
Well, at its core, the attacker leverages machine learning itself to create an attack model.
An attack model.
Yeah, think of it like this. They train a model to recognize the unique fingerprint that training data leaves on a target model.
So the attacker is essentially training a model
Mm-hmm.
to spot the subtle ways that a target model behaves differently when it encounters data it's seen before.
Exactly. It's like a data detective learning to distinguish the taste of training data in the model's predictions.
Interesting analogy. But how do they train this attack model without knowing the target model's internal workings? I mean, these commercial platforms are essentially black boxes, right?
Right, but that's where the cleverness comes in. They use what they call shadow models.
Shadow models.
Yeah, these are models trained to mimic the target model's behavior, but on known data sets. It's like a controlled experiment where they can carefully label the outputs for data that was part of the training set, out for data that wasn't.
So by training multiple shadow models and observing how they behave,
Yeah.
the attacker can teach the attack model to recognize these in versus out patterns, even in the black box setting.
Right. And the surprising thing is that they came up with several ways to create training data for these shadow models,
Yeah.
even if they don't have a data set similar to the one used to train the target model. One method, detailed in Algorithm 1, actually uses the target model itself. They search for inputs that the target model classifies with high confidence,
Interesting.
assuming those inputs are similar to the training data.
So even without knowing much about the original training data, they can still build effective shadow models.
Yeah.
That's pretty clever.
Mm-hmm. They also looked into synthesizing data based on some statistical knowledge about the target population,
Oh,
like,
right.
knowing the typical age distribution of users,
Okay.
or if they have access to similar data but with some noise added,
Yeah.
they can use that too.
So even if they don't have a perfect replica of the training data, they can still get pretty close and launch a successful attack. But how did they actually train the attack model itself?
Well, they query each shadow model with its own training data and a separate test set,
Okay.
and then they label the outputs. If the data point was used to train that particular shadow model, out if it wasn't.
So they're essentially building a labeled data set for the attack model based on how the shadow models behave.
Exactly. And this labeled data set allows the attack model to learn those telltale signs of membership.
That's pretty clever. But the real question is, how effective are these attacks in practice?
Yeah, I mean, that's the crucial point. What kind of accuracy are we actually talking about?
Right, so let's dig into some of their results. They tested this approach on various data sets and models. Let's start with something relatable. The purchase data set,
Uh-huh.
which contains records of people's shopping histories.
Interesting.
I mean, that's data you definitely wouldn't want someone knowing if it was used to train a model.
Right, sensitive information for sure.
Absolutely. So against Google-trained models on this data set,
Okay.
the membership inference attacks achieved a median accuracy of 94%.
94%. That's incredibly high.
It is. Even against Amazon-trained models,
Right.
the accuracy was around 74%.
Yeah.
And these numbers hold up even when they use synthetic data to train the shadow models.
Wow, so even without knowing the exact composition of the training data,
Right.
attackers can still infer membership with very high confidence.
That's concerning. What about other data sets?
Yeah.
Did they see similar patterns?
Well, they tested it on other data sets like CFAR image sets,
Right.
location traces, and even hospital stay data.
Right.
All sensitive information you wouldn't want easily identifiable.
Absolutely. The type of data being leaked is just as important as the accuracy of the attack. So what were some of the key takeaways from their experiments with these other data sets? Were there any factors that influenced the success of these attacks?
One key factor they found was the number of output classes in the target model. They found that models with more classes tend to leak more information,
Right.
likely because they need to, memorize more about the training data to achieve good accuracy.
So the more complex the model, the more vulnerable it is.
In a way, yes. And this ties into another crucial finding, overfitting.
So a model that's overfit to its training data
Yeah.
is more susceptible to these membership inference attacks.
Exactly. Overfitting is a major culprit here.
Okay.
Think of it like studying for a test by just memorizing the answers instead of actually understanding the concepts. You might ace that specific test,
Right.
but you won't be able to solve similar problems in the future.
Makes sense. So if a model is essentially memorizing the training data, it's going to behave differently when it sees those examples again,
Yeah,
even if it's just a prediction query. It's almost like it recognizes them.
precisely. And you can imagine how this vulnerability is magnified when you're dealing with sensitive data, like the hospital discharge data set they used. They found that models trained on this data
Right.
leaked information with over 70% accuracy,
Wow.
highlighting the real risks to patient privacy.
That's alarming.
Hmm.
It really emphasizes the need for stronger privacy-preserving techniques when working with such sensitive data.
Absolutely. It's a critical concern.
Did the researchers explore any potential solutions or ways to mitigate these risks?
They did, and one strategy that stood out was regularization.
Regularization.
Yeah,
That's often used to prevent overfitting.
exactly. And it turns out that it's also effective at reducing the risk of these membership inference attacks.
Okay, so how does that work?
Well, by adding a penalty term to the model's loss function during training,
Right.
regularization encourages the model to learn more general patterns in the data rather than memorizing specific examples.
So it's not just about improving a model's ability to generalize, but it also has this added benefit of enhancing privacy.
Exactly. A win-win situation. They also explored other techniques, like restricting the model's output to only the top few predicted classes, rounding the output probabilities,
Right.
or making the predictions less deterministic.
Interesting.
But these approaches weren't as successful as regularization.
So regularization seems like a key defense strategy here. But I'm curious, did they discuss any other potential solutions or directions for future research in this area?
They did. One area they highlighted was differential privacy.
Ah, differential privacy.
Yeah, it's a framework for designing algorithms that preserve privacy,
Okay.
and it's seen as a potential way to make models more resistant to these membership inference attacks.
That makes sense. If the model itself is inherently designed to protect privacy, it should be harder to extract sensitive information from it, regardless of the training data.
Right. The challenge, though, is that achieving strong privacy guarantees with differential privacy often comes at the cost of reduced model accuracy.
Right, that's always the trade-off, isn't it? Privacy versus utility.
Exactly. Finding that sweet spot is still an ongoing challenge in this field.
What about other avenues for future research? Were there any specific directions they pointed to that they thought would be valuable to pursue?
They emphasize the need for more research into alternative model architectures that are naturally more resistant to these attacks.
So instead of just trying to patch vulnerabilities in existing models,
Right.
we need to rethink how we design these systems from the ground up with privacy in mind.
Exactly. It's about being proactive rather than reactive when it comes to privacy and machine learning.
I like that. Proactive privacy. And it sounds like this requires a much deeper understanding of how model architectures, training algorithms, even the nature of the data itself can affect the risk of these attacks.
Absolutely. It's a multifaceted problem that requires a collaborative effort involving researchers from various disciplines, mathematicians, computer scientists, statisticians.
Right. Even ethicists.
That's a whole new way of thinking about machine learning. Speaking of different types of attacks,
The paper also distinguished between membership inference attacks and model inversion attacks.
right, there's a key difference there.
Could you elaborate on that a bit?
So in model inversion attacks, the goal is to reconstruct the actual input features
Okay.
from the model's output. Like imagine trying to guess what a person's face looks like based on a facial recognition model's prediction.
Interesting. So model inversion is trying to reverse engineer the input that led to a specific output,
Exactly.
whereas membership inference is about figuring out whether a particular record was part of the training data or not.
That's a good way to put it. Model inversion might give you an average representation of a class,
Okay.
but it doesn't necessarily reveal anything about specific individuals in the training data. Membership inference, though, directly targets the privacy of those individual records.
And as we've seen, it can be surprisingly effective, even when the attacker doesn't have access to the model's internal workings. It's a bit unsettling, really, to think that even seemingly minor details in a model's behavior can leak sensitive information.
Right. Even something like the model's uncertainty in its predictions
Oh, yeah.
can be exploited to reveal information.
I remember they talked about that in the paper. The model might exhibit different levels of uncertainty when it's processing data it's seen before versus data it hasn't.
Exactly. And that difference in uncertainty can be picked up by the attack model.
It just shows how subtle and pervasive these vulnerabilities can be.
It's not simply a matter of protecting the model's weights or architecture.
Right.
It's about understanding how the training data can manifest itself in the model's behavior, even in ways we might not anticipate.
It's a rapidly evolving area of research, for sure. This paper really highlights the importance of considering these privacy implications when designing and using machine learning models.
Yeah.
Before we wrap up, though, I wanted to touch on a specific example they discussed. The Texas hospital discharge dataset. This one really hit home for me in terms of the potential real-world consequences of these attacks. Can you tell us a bit more about their findings with this dataset?
Of course. The Texas hospital discharge dataset contains very detailed patient records, diagnosis codes, treatments, demographic information.
So highly sensitive data.
Very sensitive data. Leaking this kind of information would be a major privacy violation, potentially leading to discrimination or even identity theft.
Absolutely. What did they find when they applied their membership inference attack to models trained on this dataset?
Well, unfortunately, they found that these models were quite vulnerable to the attack. They achieve accuracy rates of over 70%.
So an attacker could potentially determine whether a specific individual's medical records were used to train the model.
That's right, just by analyzing the model's predictions.
It really underscores the point that these attacks are not just theoretical. They have very real implications for people's lives.
Absolutely. This research is a call to action for the entire machine learning community to prioritize privacy-preserving techniques.
It's a reminder that we can't just focus on maximizing accuracy without considering the potential privacy risks. We need to be responsible stewards of this technology.
Well said. It's not just about technical solutions. It's about creating a culture of awareness and responsibility around these issues.
I agree. So as we conclude our deep dive into this paper, what are the key takeaways you'd like to leave our listeners with?
I think the biggest takeaway is that we need to shift our mindset. We can't just treat machine learning as a black box and hope for the best when it comes to privacy.
Right, we can't just assume that these models will magically protect sensitive information on their own.
Exactly. We need to be proactive and build privacy protections into these systems from the ground up.
You mentioned regularization as one promising approach, and it seems like a good starting point, but it's clear we need a more comprehensive strategy to tackle this problem effectively.
Yeah, regularization is a good tool in the toolbox, but it's not a silver bullet.
So what other strategies or research directions do you think hold promise for mitigating these risks?
Well, differential privacy, which we touched on earlier, is definitely an area with a lot of potential.
Right, creating models that are inherently designed to protect privacy.
Exactly. But the challenge, as we discussed, is to implement differential privacy in a way that doesn't cripple the model's performance.
Finding that balance, that sweet spot between privacy and utility is going to be key.
Absolutely. And it's going to require some clever thinking and innovative solutions.
What about exploring different model architectures or training algorithms? Could that be a path towards more privacy-preserving machine learning?
Definitely. We might find that some architectures are naturally more resistant to these attacks. For example, models that rely on simpler decision boundaries might be less prone to memorizing specific training data points.
Interesting. So instead of trying to fix existing models, we could actually design new ones with privacy as a core principle.
Exactly. It's a paradigm shift in how we approach machine learning.
And it's a shift that's sorely needed. This research really underscores the urgency of the situation. It's a call to action for the entire field.
I completely agree. And it's going to take a collective effort to solve this problem. We need mathematicians, computer scientists, privacy experts, ethicists, policymakers, everyone working together to ensure that these powerful technologies are used responsibly.
It's a multidisciplinary challenge, that requires a multidisciplinary solution.
Absolutely.
So to our listeners, you, as experts in this field, are at the forefront of this challenge. We encourage you to take these findings seriously and consider the privacy implications of your work. Remember, the future of machine learning depends not just on its power, but also on its trustworthiness. We need to build a future where we can harness the power of these technologies without compromising individual privacy.
I couldn't have said it better myself.
Thanks for joining us on this deep dive. Until next time.